211, Lab 1, Constant Velocity. Over the course of this presentation, we'll be going over the introduction, the tracker analysis of the basketball, the initial conditions for computational model, the adjusted computational model for the experimental conditions, the observed position versus predicted position, addressing the what-ifs, meaning, and potential errors, as well as the conclusion. The purpose of this experiment was to observe the motion of the basketball moving at a constant velocity with no change in speed or direction, and use Tracker to extract the data that we then manipulated into meaningful mathematical relationships. In this experiment, I recorded the motion of a basketball being rolled on the concrete at constant velocity and analyzed the movement of this basketball using Tracker. In this experiment, the system would be considered the basketball itself, while the surroundings would include the external forces acting on the system, such as the force from the initial roll, the gravitational force, and the friction between the ball and concrete. The key concepts being covered in this experiment are Newton's first law, which states an object at rest remains at rest, or if in motion remains in motion at a constant velocity unless acted on by a net external force. It also includes Newton's second law, which describes the proportional relationship between force, mass, and acceleration, where force equals mass times acceleration. Given that the basketball is under constant velocity, it has no change in net force or acceleration, and gravitational force is canceled out by normal force. This experiment also includes the momentum principle, which states that mass times delta V, also known as the change in velocity, equals the net force times delta T, the change in time. It also includes the constant velocity, which states that velocity equals the change in x final minus x initial, or delta T, the change in time. I roll the ball from right to left, which gives us negative x values when calculating velocity, as well as a negative linear slope that can be observed in the upper right-hand corner. It's also important to note that the concrete has a slight incline, which is why I tilted the axis to compensate. The initial conditions for the computational model included updating the ball mass to 0.68 grams. We then updated the initial position of 0, 0, 0 since our ball lied at the origin. After that, we updated our average velocity calculated using the formula velocity equals delta x, change in x, over delta t, which would be the change in time, to get negative 9.91 for velocity. We then adjusted the computational model for our experimental conditions, which included updating the while loop with the max time parameter of 0.58 seconds, which was the total time it took for the experiment. We then set our net force in our experiment equal to 0. After that, we updated our velocity, which is given by the formula velocity equals velocity plus net force over mass times delta t. We then updated position, which is given by the formula position equals position plus velocity times delta t. I also included a link to the GlowScript code below. As you can see, this is the graph representing our experimental and predicted data. For the most part, there seems to be a slightly noticeable difference between our models, as the predicted line has a higher degree of linearity. This difference can be due to a variety of factors, such as the incline the ball was rolled on, as well as the divots present in the concrete. Addressing the what-ifs, meaning, and potential errors. What if the x-axis was flipped? If the x-axis was flipped, then the average velocity would be positive, and the graph that represents our experimental data would be positive. You would also see a positive linear slope that came from the origin into the upper right-hand quadrant. What does it mean? It would be possible to calculate how many pushes/pulls are added together to give zero net force. In this lab, there is no observed change in speed or direction. Therefore, the only force acting upon the basketball are the gravitational and normal force, which end up canceling each other out. Some possible potential errors in this experiment include the non-centered mass points that we did on Tracker, as well as the surface the ball was rolled on could have been steeper than what the x-axis was set to. Additionally, the surface possibly could have altered the direction and gave us not a constant velocity. In conclusion, this experiment demonstrates the meaningful relationship shared between an object's position and time when under a specific set of conditions, such as constant velocity with zero net force. As we have observed in this experiment, when at constant velocity, position and time share a proportional relationship that can be represented as a linear function, which allows us to predict the future behavior of a set system given its surroundings. Thank you.